Hello and welcome to my presentation on the topic of longest common subsequence, and we will use the approach of dynamic programming to solve this further. So let's move on. Before we move further, I would like to give a brief introduction, or we can say a brief flow of the whole video, how it will proceed. First of all, we will be discussing the theoretical concepts and terminologies behind the question. Then we'll move on to its algorithmic implementation, and at the end, we'll be analyzing the time complexity for the algorithm. The solving approach, as I mentioned earlier, we'll be using dynamic programming as it is the most efficient one among other approaches and uh, uses and takes less computational time. So moving forward, first of all, we need to understand the theoretical concepts, and in that, uh, the first question arises: what is a subsequence? So the basic definition which tells about subsequence is that a subsequence is a sequence that appears in the same relative order, but not necessarily contiguous. I tried to explain in simpler terms. Subsequence is a sequence that can be derived from another sequence by deleting some or no elements without changing the order of the remaining elements. See, we have to note the last line, which is very important, without changing the order of the elements. So what this means, uh, we'll understand in a much better way while taking an example. Say for suppose we are given a sequence of characters A, B, C, D, E, F, G. We can see uh, the subsequence of this sequence are A, B, C, A, B, G, B, D, F, like so. I'll try to explain this. See, A, B, C is a subsequence of say of this parent sequence, which is A, B, C, D, F, G, because we have taken A, B, C in order and deleted some of the elements from the parent sequence. So important thing to note here is that we are not disturbing the order of the characters. Similarly, in the second example ABG, we can see we are not disturbing the order of ABG. First A appears, then B appears, and then G appears. So in between we are deleting the elements C, D, E, and F. So in this way we can find the further subsequences of the given sequence of characters, right? So this thing is clear to us. Now recalling our 12th class concepts of permutation and combination, we can say that a string which has characters n there, or we can say a string of length n, will have 2 to the power n different possible subsequences. So now that we have clearly understood what a subsequence is, it's time to understand what a common subsequence is, because this is the one of the most important concept which we have to learn in order to understand the problem further. So suppose we are given two sequences x and y. We say z is a common subsequence of x and y if and only if z is a subsequence of x and z is a subsequence of y. What I mean by this? Uh, Z is a subsequence of X only if Z has its characters which are common to both X and Y, uh, and noting that they appear in same order, right? Once again, to understand in a better way, we'll take an example. Say for example, we are given strings X and Y with uh, characters A, B, C, B, D, A, B as X string and B, D, C, A, B as Y string. We will iterate from the left hand side and move till the uh, end of either of the string, and after that we will stop. During this procedure we will try to find the common characters occurring in both the string, and we will mark them. So the marked one will be extracted out, and that will result in subsequence. What I should say is common subsequence. So moving from left onwards, we see that B is the first character which appears to be common in both X and Y. Then C appears to be common, then B, and then A. Note, now that we have reached till the end of string Y, there is no need to compute further. Therefore, We will not move ahead and stop at this point only. So now that we have clearly understood the basic concepts and terminologies, it's time to move to the problem section. As we can see, we got the result as BCBA, which is the subsequence. The problem. It says given two sequences x and y over a set S, the longest common subsequence problem asks to find a common subsequence of x and y that is of maximum length, right? So this question will be given to us, and with that, the input will be string x and y of length m and n respectively. After that, we have to compute the common subsequence among from we have to extract the common subsequence from these two uh, given strings. So the first question which usually comes in our mind is that why did we choose dynamic programming? It is because one of the approaches uses recursive method, but that takes exponential time. But obviously, we don't need that. We need an efficient one, right? So we will further observe how this dynamic programming algorithm improves the overall efficiency and thus reducing the computational time. We will follow the usual table format used in dynamic programming and use the bottom-up approach to get the final result. As you can see, we have displayed a table below. In that we can see indexes from 0 to 4, and we can see the characters of two strings uh, respectively arranged from index 1 onwards. Then what we need to follow is fill the 0th index row and column with 0. As you can see, I have already filled it with 0. Then start filling the string elements from index 1. There are some rules which we need to follow in order to fill this table further, which is to start from the first row element, then we will match it with the elements of each column. If it matches, then add 1 to the preceding diagonal element and store it in that cell. What I mean by this, I will just show you in a minute with an awesome animation. Otherwise, the second condition will be uh, uh, compare it with its left and upper numbers and choose the maximum among them and fill in that cell, right? So in the next part, I will show you this animation and give you a better idea how this thing is implemented.
As we can see, we have started with the element of row 1, and now we will compare it with the element of column 1, which is A. We can see that both of these elements are equal. So we will follow the rule 1, which is we will take the diagonal element, this which is colored in the yellow, and we will add 1 to this and append in this column, right? So 0 it is here, we will add 1, we will get, what we'll get? We'll get 1 and we will append it here. So this is the method that we have to follow for rule 1. Now for rule 2, let's suppose again we take the element in row from the row 1 and we now compare it with column 2, which is A and X. As we can see that both of these elements are not equal. So what we'll do, we'll just compare these two elements, and maximum among them will be appended in this column. As we can see, maximum is 1, so 1 gets appended here. So in this way we can get the intuition behind the approach of dynamic programming and rules which have to be followed. So now further we will be taking another example, and step by step we'll see how to implement it and get the final result.
Dynamic programming approach and its implementation. So uh, this is the best part which I like about this video. So I'm excited. So let's move on. So we are given with a table. That is, we first form the table. Suppose we are given with a string x, which is having characters as a, b, c, b, d, a, b. We'll mark the indices on the table as 0, 1, 2, 3, 4, 5, 6, 7 along the x-axis to represent the string x, right? So we will append the characters of string x from index 1 as shown below. And we are given with another string which is y. So again repeating the same steps, marking the indices from 0 to 6, and then appending the characters of string y from index as shown here. So now the first step for dynamic programming approach occurs, and we can see that here's the algorithm which tells us that m is a variable which stores the length of string x, and n is another variable which stores the length of string y. Then we can see there are two for loops, one in which I starts from 0 and moves on till n. N is what? Just we can see that n is the length of y, and then in that for loop it assigns 0 to each and every row starting from I till n. Similarly, for the second loop, we can see that j starts from I. Why it is starting from I? It is because in the zeroth column we have already filled 0, right? So j starts from 1 and moves till the length of x, which is m, and assign 0 to each and every column of that row. So our initial steps are completed. So it's time to move on to the second step of filling the table. So now that we have clearly understood the first step of this implementation, now it's time to move on to the second step for filling this table, right? As you can see, there is an algorithm displayed on the right hand side. It is the same algorithm which I discussed with you guys from the previous slide while I was displaying an example and filling the table. So now we will just move on and see the animation and try to fill the table. In this way, we will get a better intuition and understanding of how the algorithm is working, right? So let's move on. As we can see, we have chosen a element from row 1 and element from column 1, which is B and A. We can see it both of them are different. So which condition will be followed? We can see else condition will be followed, this one. What it will do, it will check elements on the adjacent cell, which are these two elements, and the maximum among them will be appended here, right? So we can see the maximum will be 0 only, so we can see 0 is appended, right? So now we can see that B and B, these both elements are same, correct? So now we can see the if condition will be followed, and what it will do, it will take the diagonal element of that cell and add 1 to its element and append it here. We will see 1 appearing. So now we'll move ahead. We can see this B and C are both different, so else condition will be followed. uh, Greatest among them will be appended in this block, so we can see 1 is appended. Moving forward, we see both B are same, so we'll take this diagonal element, add 1 to it and append like this. Moving forward, B and D, these both elements are different, again taking maximum among these two and appending here in the column. We can see one is appended. So moving forward, again different characters. So again taking the maximum and appending like one. Uh, Moving forward, you can see both of these uh, characters are similar. So we'll take the diagonal element and add one to it. So we will get one here like so. So we will do the same steps in all the rows and columns. So let's move ahead and faster and complete this whole table. Again, these both are different characters. So taking the maximum of the two adjacent cells, which is 1. Different characters taking a maximum, appending 1. Again, different characters taking the maximum of these two, which is 1 and appending. So these two are now similar, and we will take the diagonal element, which is this one, add 1 to it, which after which we will get 2 and append it here like this. Moving further, we see these two elements are different, taking the maximum of these two. So we get 2 as the maximum one, so we append it here. Now again we see D and B are different, taking the maximum of these two. We get 2 as the maximum one and append it here. So now that we have clearly understood how this procedure goes on, I will just quickly fill this table and meet you guys at the end when this whole table is filled up, right? As we can observe now that the table is completed, and once we have completed the table, it's time to calculate the what is the length of the subsequence, which is maximum, right? So the maximum length of the common subsequence is 4. How is that so? Just look at the rightmost, right bottommost cell, which is 4 here, right? So one thing to remember is that after completing the table by the specified rules, we will get uh, the maximum length of the subsequence as the number present at the bottom rightmost cell, which is 4 here, right? So why not to find what are the elements for the common subsequence, right? Uh, so let's move on. First, we will circle this bottommost element 4 here. We can observe that this 4 would have come either by taking the maximum of these two red colored 4s, or by adding 3, or by adding 1 to the element diagonal to it, which is 3. So by the table we can observe that A and B were two different elements, so this 4 would have come only by taking the maximum of these 4. So we can either move in up direction or the left direction. I choose to move in left direction, right? So we now moved in the left direction. Now we observe that this 4 uh, would have come only by adding 1 to the diagonal element, which is 3. So we move in the diagonal uh, position. Now we closely observe, so we see that this 3 is the maximum of 3 and 2, so we move to left. And now this 3 is appended by adding 1 to its diagonal element, which is 2. And this 2 is appended by taking the maximum of 1 and 2. So we move in upward direction. And now this 2 is appended by adding 1 to its diagonal element. So we move in diagonal direction like this. And this 1 was appended by taking the maximum of 0, 1. So we move in upward direction. And this 1 was appended by adding 1 to its diagonal element, which is 0 plus 1. So we move in that diagonal element, right? So we have made a path which we have to follow, and in the next step I will uh, teach you how to uh, uh, extract the elements of that subsequence, right? So now that we have completed and specified the steps which we have to follow in order to extract the elements for the subsequence, we will follow some rules and extract them. We will encircle that cell from which we took the diagonal step upward and append the element corresponding to that cell in the subsequence list. So let's move forward and observe. We saw that 4 we saw that cell number 6 comma 6 was having the element 4, and from that column from that cell uh, we moved in diagonal direction. So we will append the element corresponding to that cell, which was A, to the subsequence list and move ahead. Then we saw cell number 5 comma 4, which was having element as 3, uh, was the cell from which we took the diagonal step. So we will append element corresponding to the cell which was B, and then similarly we will append C and then B. In this way we got the final output characters of the subsequence list. So in this way we have completed the algorithm and its implementation, and now we will be discussing the time complexity of this algorithm. So now that we have got the result and we have reached to the end of this video, it's time to analyze the time complexity for this algorithm. As earlier we saw that algorithm was having two nested loop. The first, that is the outer loop running n times and the inner loop running m times, while the content inside this loop uh, which were done in a constant time unit, right? Thus the total time we can say is big O of n m, which is clearly we can say is very efficient as compared to the recursive approach as that was taking uh, exponential time, right? So this is the end of this video, and I hope that I have discussed each and every concept related to this problem and made them understand in a better way with the help of animations. So thank you.